Hey, good morning, everyone. Welcome back to class and welcome back to school. I apologize for not being with you today. So, as we talked about before, you have to be gone today. So you are blessed to have a sub, and you're also blessed to have this video I created for you. So, hopefully you enjoy it. I know it's going to be a little different, but I trust that you can work with each other and you can get through everything on here and hopefully pick up some things without myself being here. And so help each other out. It's kind of long. I warn you now. The sub, I asked if they would pause the video as we go along at different places so you can try things, write things down, and do it on your own before we move on. So if the sub hasn't passed out, so pass out the bell ringer sheets or pull them out, I guess, if you have them already. But here's what I'm going to ask you today is, could you go back to last chapter? Could you graph these following piecewise functions here? So you have a function and it has pieces, and take a moment, see if you can graph it. If you wouldn't mind pausing the video, that'd be awesome. And you guys try and see what you remember. Help each other out. Okay, I assume you have this completed and tried it. So again, what you remember, hopefully, is if I have a function, I'm going to start at the top one. That looks kind of weird. It's a line, but I can rewrite it so that it looks like negative x plus 1. And then it's easier to see my y-intercept is 1. And then my slope is really 1 over 1 or negative 1 over 1. So if I start at 1, and this says I have a slope that's going to go down 1 over 1, down 1 over 1, down 1 over 1, and so forth. I can draw a line through those points, but the only stipulation again is this is piecewise, and I have to make sure I draw my line for only x's that are less than or equal to 1. So 1's right here. And so I'm going to start there, and I'm going to draw everything that's less than that as I go this way. Not a very straight line, but it's a line. The second function is also another line. This one, though, has a y-intercept of 1, which is, hey, the same place, but a slope of 2 over 1. So this one says I go up 2 over 1, up 2 over 1. And this one, though, I want to start graphing at and only exists for anything greater than 1. So if I start at 1, and 1 again being right here, I would start at its 1 value, and I'm going to go and follow this up and through where we're at. Now the only thing I didn't do that's quite right is this does not have an equal sign to it, so hopefully your graph will have, like my graph has now, has a hole right there. And so I have a value, I have a graph that looks like this. So it's a piecewise function, and again, breaking up the pieces. So hopefully that was something you remember from before and that you can still do, even this morning. Now, I, again, dislike being gone, but today I'm going to ask you this. I want to take you through some pieces and parts about polynomials, and we're going to look at their graphs, and what polynomials are, and I guess what their graphs look like, and how we can find special properties about them so you can graph them and you can answer various things about polynomials. So you're going to look at some properties of polynomials. You're also going to graph these polynomials based upon those properties. And so when you walk out here today, hopefully you feel confident doing those two things. So again, as we go through the video, please stop it if there's anything. As students write down examples, stop the video. So time to work. Treat this like class time. So I was going to ask you, what is a polynomial? And here is what the book is going to say. Looks pretty neat. Looks pretty simple. Probably not. Maybe Douglas likes it. I don't know. But this is how you write a polynomial. It's some number times x raised to some power. Maybe it's the 5th power. Plus or minus some other number of x raised to a different power. Plus or minus some other number I don't know, for x raised to something else, minus or plus 1, whatever it might be. But you have a list of all these things where you have x raised to different powers, we have different pieces with it, but this is a polynomial. We're going to spend the next week-ish looking at polynomials. Here's a different example that I wrote down before of 5x to the fourth minus 7x to the third minus 3x squared plus 2. What makes polynomials so special and why math people really like them is the fact that when you graph them, they're always continuous. They never stop. There's never any place where they're undefined or where you have vertical asymptotes or holes in your graphs. There's no jumps or steps in the graph. They're always continuous. They go up and down, and they do different things. And we can analyze and look at some properties with them and be able to graph them based upon those properties. If you look carefully again at this, one other special property that I should mention is every power of a polynomial, no matter what, and this one would be like x to the 0, every power that your x has, again, is always a positive. It's always a whole number. You never have negative exponents. You never have fractions for those powers, so they're always whole numbers, and that's one defining characteristic of a polynomial. They make really sweet graphs, and in calculus, we like polynomials because they allow us to analyze any kind of function with them. Take a moment, it might be a good time to pause the video. I want you to jot down these 3 basic degrees of polynomials. There's all sorts of degrees of polynomials. For a first degree is a line, a second degree we call a quadratic, a third degree is called a cubic, fourth degree is quartic. You can have 5th degrees and 6th degrees and 7th degrees of polynomials. And we're going to talk about what that means. It's the degree or the biggest power of any part of my polynomial equation, gives it its degree. So take a moment, write this down, and if the sub will pause it here, that'd be great. And in a moment, I can explain kind of more what these things say and what they mean. So, as you wrote this down, and now take a look and see if this makes sense what you mean. Hopefully you remember that quadratics, or what we call parabolas, they're a second degree. So it's like having, an x squared plus 2x minus 1. That's a quadratic or a parabola. And they always look like this. There's 2 branches on them. And the reason why there's 2 branches is because they have a degree of 2. The biggest degree is 2 here. When I say branches, I think of this. It's like this is a branch and this is a branch. Going up and going down is a branch here. Those are 2 branches. Quadratics have 1 extreme point. We call that the vertex. In this case, it's the highest point on the graph, and that's my 1 extreme point. I can't have 2 extreme points, only 1 if I have a quadratic. And the unique thing about quadratics is they will only have at most two zeros. So the key word is at most here, but they'll either have 2 zeros or they're going to have 0 zeros. They'll never have 1 0, but they either have 2 or 0. So in this case, this crosses, when I say a 0, that's the x-intercept. This has 2 of those, or I could draw a parabola that looks like this, where it's never going to cross the x-axis, and that would be a case where it has 0 zeros, but it's either 2 or it's 0. Looking at the cubic one, for instance. A cubic one, it's a 3rd degree, so I have something to the 3rd power, plus whatever, minus whatever as I go through, but the biggest degree is going to be x cubed. This, though, has 1, 2, 3 branches always. It has 2 extreme points, and so if you see it has a high point here and a low point there, so if you are asked about extreme points, how does that relate to the degree? It's always 1 less than my degree. So if my degree is 3, I'm going to have 2. If my degree was 2, I add 1, so it's always 1 less than my degree. And this says, and again, the key word here is at most 3 zeros. So if you look at my graph, this crosses the x-axis once, twice, 3 different times as 3 zeros. And again, I'm not here with you, but I'll ask this question anyway, is how else could you draw something with 3 branches like this and 2 extreme points so that it only have 1 zero? Would that be possible? Well, come on now, you can't all be sleeping right now, right? At least one of us has to be awake right now. Hey, thank you. Is that Parks back there? Hey, thank you. Yeah, you could draw something like this. You could go up, down, something like this, like where I would have just 1 0 here, so that's the same graph. And so I could have either 3 zeros or 1 0. I can never have 2 zeros. It's either going to be 1 or 3 to have zeros where they cross the x-axis. And last, again, not the least, hopefully you're seeing these same patterns here. If I have a quartic, it's a 4th degree. You have the same number of branches, 1, 2, 3, and 4. And looking carefully at this, notice the extreme points. This has 3 again, 1 less than the degree. So you have 1 here, 1 here, 1 here. So the more degrees I have, the more ups and downs I have. It's more of a roller coaster that my problem is. Now this says, again, at most 4 zeros, because that's the same as my degree. So this one has 1, 2, 3, 4. So I have 4 there. Could you draw a quartic function with less than 4 zeros? Yeah, I can make the same looking shape here. I could do something like this. That's got 3 branches, or 4 branches, sorry, 1, 2, 3, 4. Does that ever cross the x-axis? No. So this would have 0 zeros. So I could draw one like that. Oh yeah, no, you're right. Who was that back there? Thank you. Yeah, I could draw one maybe like this. So maybe it does this. It goes down, goes up, but then it does this. It goes back up again. This is going to have 1, 2, just 2 zeros. And these other ones don't. But notice again, I have 1, 2, 3, 4 branches yet, so it's quartic. But I could either have 4 zeros, 2 zeros, or no zeros. So I don't know if you see the pattern with zeros based upon the degree. So they always come in pairs of 2 when I have my zeros here. So there's always a difference of 2 between my options of what I have as I look and go through. So some of that's going to be important for you in a moment too, as you graph these, to understand the degree has a big influence on zeros, has a big influence on the vertex, or how many extreme points, and also on the number of branches. This I stole from your textbook. You'll find the same graph in there, page 257, as it says up on top here. But one other thing that's huge in terms of graphing polynomials is understanding the end behavior. Now, looking at the pictures that's in the book and what's on the board right now, maybe take a moment and start drawing and writing these down. And again, today I apologize. There's a lot of little properties, and you're going to draw lots of stuff, so it's probably more notes here. It's probably good that I'm not here, so you're not frustrated in front of me with it. But as you look at this, I'm going to point out a couple things with it. I really have kind of two pieces here. On the left-hand side, this is if I have a polynomial that has an odd degree. So look carefully at that. So if I have a polynomial that has an odd degree, so if I have a degree of 3 or 5 or 7, anything that's odd, even 1, a degree of 1 is a line. This would be true for a line as well. My polynomial, notice it either starts out negative and it ends positive. So it starts out going down but ends going up. Or it starts out going up but ends going down. And so I have one of these cases though, but if it's an odd, it's either going to start high and end low, or it's going to start low and end high. It's never going to start and end in the same place. Now compare that a little bit. I go to the other side. If I have an even degree, so thinking like something to the second power, fourth power, sixth power, anything that's even, what's different about these is it either starts up high, ends high, so it starts and ends the exact same, or it's going to start low and end low. And so I have one of those cases. So if it's even, you're guaranteed to start and end the same, whether it's a positive or a negative, you're going to start and end the same. If it's odd, you're going to it's going to change as I go from left to right, as I go throughout the function. The other thing that's interesting on this to look at as well is, how do I know how it ends and starts? How do I know this starts out negative and ends positive for this first one? I know based upon the leading coefficient. So if my leading coefficient is positive, so that means if I had, say, something like 3x to the third, 3 is a very positive number. X to the third, that's an odd degree. Anything that's positive, that tells you actually how it's going to end right here. So because it's an odd degree, I gotta change from negative to positive or positive to negative, but because my leading coefficient, this number in front of my x, is positive, that tells me I'm gonna end on a positive note. I really hope today that you are a positive leading coefficient, so no matter if your day was good or bad, you're gonna end on a positive note today, what it might be. The other piece that's different is if my leading coefficient is negative, that tells me that it's going to end negative. And so even if it started positive like this one did, it's ending negative. So maybe I have a negative of 4x to the third again. Again, that's odd. But because this is negative right here, it's going to end negative. So that leading number tells you how it's going to end. And the same thing's true over here on the other side with even degrees. Again, if I have a positive leading coefficient, notice it ends positive. And because it's an even degree, it started positive and it ends positive. Hopefully that's how your day's going. You had a positive start to the day, and you're going to end with a positive end to the day. And if it's negative like this one is, same thing, it ends negative, but because it's even, they have to be the same, and it would start out negative. Hopefully that's not how your day is going, where you started with a negative and end with a negative. So I'm going to come back to that in a moment, but that's kind of huge in terms of getting a general idea of how my graph is going to behave starting and ending. It's all about what kind of degree, odd or even, and it's all about the coefficient in front, whether it's positive or negative. So, I'll put you to the test now. Enough of Mr. Roy blah, blah, blah in here. I want to know, there's two of them here. Determine what the degree is. So how do I know what the degree is? What would its leading coefficient be? And then can you describe or show what the end behavior is going to look like? So we'll check for learning right now, see if you caught on what I was trying to throw your way. Stop the video, let them try it. Thank you. Hopefully you had a chance to look at it and do this. So if I asked you these questions, what's the degree of the first one? Well, the degree is the biggest power. In this case, it's a degree of 5. So that means I'm going to have 5 branches. I'm going to have 4 extreme points, up to 5 zeros, maybe 3, maybe 1. What might be? My leading coefficient is actually going to be the number in front right here, and that's a positive 4, or a 4. Now, based upon just those two things now, what's the end behavior going to be? Is this function starting on a bad day, ending on a good day? Is it starting on a good day, ending on a good day? Well, how I know again is my degree. This is an odd number, so that tells me it's going to either start good and end bad, or it's going to start bad and end good. But this 4, because it's positive, tells me that it has to end positive. So no matter what it does in between, you know, it could go up, down, whatever it does here, it's got to start, or it has to end positive, and because this was odd, it had to start negative. So I don't know what's happening in between and what's going on there, but it's negative to start, positive to end because it's odd, and it ends positive because it's positive coefficients. Hopefully you have the same answers. What about B? B, same thing. So what's my degree? So degree is going to be a 4. That's the biggest power. My leading coefficient, that's going to be a -2, which is negative. And then the last thing then, what's my end behavior? My end behavior just tells me that my polynomial, in this case because my degree is 4, it's going to be the same. But because this is negative right here, it's going to not have such a good ending. It's going to end negative. And because this is an even number for a degree, it has to start -2. I feel bad for this polynomial. It started negative. Whatever it's doing in between, it's going to have, 1, 2, maybe something like this. And I don't know what that looks like, but it's going to start negative and end negative because of these characteristics there. Sure. A few more things. The last really piece that's going to be of great value for you, and then we're going to do a couple examples together, and I promise I'll end this because I know this is going to be kind of a long lesson, but the last property that I need you to look at and understand is this. There's different types of zeros that you can find. In the word in math, and we find these different levels of zeros is the word multiplicity. You could have, if you look at the one on the left, and I made up my own names for these. These aren't book names, but I find it easy to remember, though. You could have the first one, which I call the slice, because that's what it does. It's a single multiplicity is what the slice is. And so this has a 0 right here at x equals -1. That 0, though, it comes from my function just slicing through. It just slices through there. This has also a 0 here of x equals 1, and that's also just a slice. It just slices through there, and so I call it a slice. The reason why we call it a multiplicity of 1 is if I wrote, say, this 0 down as a root, it's going to be written as x minus 1 is how we write it, but it has a degree here of 1, and that's why it is a multiplicity of 1. This one over here, same thing, I'd write this one as x plus 1. Again, it's always the opposite what it looks like. We kind of talked about the transformations last chapter, but this would have a power of 1 there as well because it's a single slice that goes through the graph. So when your graphs slice through, they have a single root at each of those places. Now that's different than the middle one, which I call the bounce. If you take a look at this graph, it's like a basketball here. It goes down and it bounces right here. It hits the axis and bounces up. That's a 0, and that 0 is at x. I'd write it as x minus 1 because it happens at 1. But what that really means, because it bounces, that tells me that this 0 has a multiplicity of 2. It actually has 2 roots that are exactly the same, and it's got like a double multiplicity or a double root that's exactly the same. You have an x minus 1 times an x minus 1 or an x minus 1 squared. That's a double, it's a bounce. So anytime my graph bounces, that's a multiplicity of 2. So it's only one location, but there's actually 2 zeros hidden in that one location. They're just the exact same. The third one's the weird one, the weave. I couldn't think of a better name for this. So the slice makes sense. You slice through things. The bounce, it bounces kind of back off the axes. The weave, it does a little juke and jive. So my graph, if you look carefully, it's going up, and then it kind of like stalls out, and then it goes back up again. It kind of jukes and jives right here. That's a characteristic of something with a multiplicity of 3. So at the same value at 1 here, so I'd have x, again, minus 1 if I wrote this. That has a multiplicity of 3, so that means you actually have 3 of the same zeros in the same location, and it causes my graph to make a little juke and jive, a little weave in the graph. And so you have the weave here. So the slice is a single, you have a power of 1. The bounce, you have a power of 2, you have 2 of them there, and it makes the bounce. And the weave makes a little zigzag there with it, what it might be. Now if you had, like, let's say a multiplicity of 4, those start to look a lot like the bounce, actually. It takes on that characteristics. If I have a multiplicity of 5, so I have 5 at the same, those start to take on and look like the weave, and they kind of go back and forth, but you don't see a lot of those in textbooks that you have to deal with. So, last but not least, one more thing to write down and then some examples. In a moment here, I'm going to ask you to graph a polynomial. So I'm going to give you a polynomial and I'm going to say go to town and graph what it is based upon all these things that I just tried to show you. Up here, I wrote down some of the guidelines, things to look for. So how do you find zeros? Zeros come from my factors and setting them equal to 2, 0. And I'll show you what that means in a moment. Finding certain test points, like finding the y-intercept, which means I need to set x equal to 0. So find what the y-intercept is. Sometimes I have to make a little table, sometimes, some test points, and you just have to plug in some points and find out what they are. But the other biggest thing that we're going to focus on is the things we looked at before, is the end behavior. So what's its degree? What's its leading coefficient? You can say a lot about my function based upon just that. And then you kind of just put all those pieces together and make the graph. So again, maybe pause the video, give them a chance to jot these 4 steps down, I guess, for graphing, but these are things that I'm going to lead you through that I need you to be able to do. Thank you. Here it is. A couple examples, and we will, I promise to stop here for you. So, first example, they're going to ask you to graph this. Well, if we go back to what we already know a couple things. The degree here is 3. My leading coefficient, what's really in front right there? Yeah, it's just a positive 1, so it's positive. If I asked you this question, what's the end behavior? Well, you know, hopefully, again, that if I have a degree of 3, it's going to start and end differently, but because this is a positive one here, it's going to end going up and it's going to start going down. And so somewhere in between it's going to do something like this, but that's kind of the characteristics of my end behavior. Oops, I had to write a negative there. How about a positive, Mr. Roy? Now define some kind of more specific details about this than just the general sketch of it. If I want to find zeros, what I need to do is I need to set this equal to 0. And now this is where, again, last chapter we spent some time on factoring. We need to factor and find all the factors, all the pieces that come into play. And so if I factor this, the one thing I can do is I can take out a GCF of x, so I'm left with x squared plus 2x minus 8. And if I kept going with this, I could have still my x, but this trinomial here, 2 things that multiply to be 8, but then add to be or subtract to be 2, I could have x and then a positive 4 and x and a negative 2. And so when I ask you now, what are my zeros? My zeros here are this, this, and this. So if I set x equal to 0, well, my answer is that, x equals 0. If I set x plus 4 equal to 0, my answer is going to be x equals negative 4. If I set the last one, x minus 2 equal to 0, I'm going to get x equals 2. So I'm just adding the 2 over. And so I get 3 different zeros in this problem. So if I want to graph this and start making kind of a point to look for, draw my best looking graph that I have here, there it is. I could plot these things on my graph. I know that this zero has to be a 0. So I have a 0 there. I know that's -4, so -4 also has to be a 0 of some sort. I know that 2 over here has to be a 0 here too. So I know that my graph crosses there. Now if I look carefully at each of these though, this one is a x to the first, that's a slice. So that's going to make a slice because it has a multiplicity of 1. This one is going to be also a multiplicity of 1, so a slice. And the last one, because I just have one of them, is also going to be a slice. So all 3 of these zeros are going to be slices. They're going to slice through my graph. The only other thing I might have you find and do here too is those are zeros. I'll put it right here. This is another easy one to find is what's my y-intercept? And that just is making x equal to 0 here. So what happens if I go back up to the original function, if I make all my x's 0, this is going to say like y equals 0 to the 3rd power plus 2 times 0 to the 2nd power minus 8 times 0. This is kind of simple, but what's 0 plus 0 minus 0? You're going to get 0. So I have a y-intercept of 0. And you actually already see that right there in the middle. That y has to be 0. It's going to have a y-intercept there at 0, which we already kind of maybe knew a little bit. So putting this all together, my end behavior, my zeros and my y-intercepts, I know it has to start out negative. I know it has to end positive. I know it has to slice through this. It's going to have to slice through that one. And it's going to have to turn and slice through that one. I'm going to get a graph that's going to look something like this. Again, the only thing I don't know right now is how high this goes, if this goes up higher or if it goes down lower. And to be truthful and honest, I am not going to be picky about caring. I just want the general idea, and if you can find the actual zeros and what type of zeros they are, that's all that would matter. I think, yeah, so like, this is what the graph is supposed to look like. Does that look like our graph, roughly? Yeah, sure. One more for the sake of us here to go through and do. Write this one down. You try this one and see how much of this you can do on your own. So if the sub would pause this, try this one out. Now think about how you factor 4 terms. So we talked about last week, how do you factor 4 terms, what that looks like. So hopefully you've tried this. If I want to factor this, the way to try this one, 4 terms, is to try the grouping method. So if I factor this and set equal to 0, I can take a GCF of x squared out, so I'm actually left with x plus 3. On this other one, here I'll use a different color here, if I took out a -9, I'm actually left with x plus 3. So the one thing they both have in common, they both have an x plus 3 and x plus 3, so that's one of my factors. X plus 3 is a factor. The other factor is x squared minus 9. Oh, but wait, x squared minus 9 is really x minus 3x plus 3, difference of cubes, or squares. And if you look carefully though, notice these are the same, so if you want to get clever with this, x plus 3, this is x plus 3 squared. And and this is x minus 3 to the first. So what are my zeros here? 1, 0 is going to be, set that equal to 0, I'm going to have x equals negative 3. Is that going to be a slice, a bounce, or a weave though? So this would cause a bounce in my graph, multiplicity of 2. This would be positive 3, and that would create a slice in my graph in a moment here. Off on the side, my degree is, go back and see it all here, my degree was what? 3. My leading coefficient is 1. So that means my end behavior, sorry for all the abbreviations, my end behavior though, again, is going to end going up. It's going to start going down, and it's going to do something in between, kind of like the last one. That's what cubic functions look like. And if I found a y-intercept, again, that just means make my x's 0. If I make all these things 0 here, I'm going to get y to be 0 plus 0 minus 0, but then minus 27. So if I simplify all that, I'm going to get y equals negative 27 for my y-intercept. So it really just ends up being this number on the end is my y-intercept. So the graph of all this, put this together, the graph should look like this. I'm going to have at negative 3, I'm going to have 1, 0. So at negative 3, there's 1, 0. And that 0 is going to be a bounce. I got to remember that. Also at positive 3 is going to be another 0. So positive 3, another 0. My y-intercept is going to be way down below here at negative, pretend with me that's negative 27 down here. So that's going to be way down there. So I got to cross that y-axis down there. And then now based upon my degree and end behavior, I know that my graph has to start going up. Sorry, it has to end going up. It's got to start going down. And it's going to do something like this. It's going to go up. It's going to not cross here because it's a bounce, so it's going to bounce off there. It's going to have to go down through there somehow, and then it's going to have to slice through the last one to get a slice there. So I'm going to need a graph that looks something like such. And again, is that perfect? No, but it's close. The actual graph looks something like that. Again, that's zoomed a little bit differently, but see how it bounces here, slices here, goes through negative 27 down there. But a similar idea. So I'm going to stop there because I know you have to be tired of looking at this and taking notes. Ignore this first. We'll pick this up in the days to come here. Now I'm going to ask you this. This is not a lot. They're all odds. You can check your work though, but take your time. Help each other out. I know there's, some of us, again, math's not our favorite, but I know there's a lot of us that are really strong and do well with it, and hopefully this made sense for you. But be a good neighbor, be a great classmate, and help your fellow classmates out if they have questions. Blessings on the rest of your day. I thank you again for your time. I'll be patient. Again, I'll be around if you need help in the morning. But good luck.